Okay, we just did the experiment. Now let's see how we can solve that using our equations for photoelectric effect. So we have two different versions of the equation that you should have on your sheet. E photon is equal to W plus kinetic energy of the electron, and H nu photon is equal to H nu naught plus kinetic energy of the electron. And the other thing that's really important to note is that these are in fact sort of the same equation, but just plugging in different equations. So when I write this out, I think it's useful to remember that the energy of the photon over here, we can use any of our equations for energy of a photon. H nu photon, or again, if we wanted to, we could also say this is hc over lambda of the photon, because that's one of our existing equations for the energy of a photon. The energy of the photon is h nu is equal to hc over lambda. So we could use that for the energy of the photon if we want or need to. And then over on this side, remember, this is all about the photon. So in this case, this sort of purple photon or light coming in. This is the electron that's ejected. So this is telling us about the electron that's ejected. And this W here is the property of the metal, right? So that's the binding or threshold energy. And again, that W is equal to H times nu naught, where nu naught is the threshold frequency of the metal. We can see how that works by noting that when E photon is equal to W, what happens? So if E photon is equal to W, we have W is equal to W plus the kinetic energy of the electron. In that case, we can subtract W from both sides, and we get that the kinetic energy is equal to 0. And this is the case when we're at threshold. Because at threshold, there's no kinetic energy of the electron. Here, there's maybe a tiny bit, but in theory, there's no kinetic energy, and all the energy from our photon went right into overcoming that binding energy in the metal. And so we can say here that, again, when we use that threshold, there's 0 kinetic energy, and in fact, at that point, the energy of the photon is just equal to W if we're using the threshold photon. And the energy of the photon is h nu naught is equal to hc over, we could view it as like lambda naught is equal to W. So you can think about that a couple different ways. It's certainly valid to use this one. Maybe that's a good way to solve it initially, is to say that, okay, this is threshold, the place where the electron ejection begins. We should recognize that this is the threshold frequency or wavelength. And we can go from there to get the binding energy. Okay, so here 427 nanometers is our threshold wavelength. In this equation, as we're given it, we have the threshold frequency. So maybe one good way to do it is to go from the wavelength to the frequency. That's this equation. C is equal to nu lambda. Again, I could put the subscripts on there, like a naught there, but it doesn't really matter. It's anytime I have a wavelength and I need a frequency, I can go back and forth with this equation. So I want to solve for frequency, so I need to divide both sides by wavelength to get frequency by itself. Okay, so plugging in here, C over lambda. Again, checking our units, meters cancels, and we do get things in 1/seconds. Remembering we have to always convert from nanometers back to meters. This is what it looks like on the calculator with that small capital E to represent scientific notation. And we get 7.03 times 10 to the 14 hertz. I'd encourage you not to round until the end, but that is, again, hertz or seconds to the minus 1. Now that we have the frequency, and it's valid to call this the threshold frequency because that was the meaning of that whole sentence about how we found it. We found where we had just enough energy to eject the electrons. Now we can plug that into our equation up here. H from your list of constants is 6.63 times 10 to the minus 34 joule seconds. And nu naught, 7.03 times 10 to the 14. And again, you can call this hertz or seconds to the minus 1. Maybe I'll use seconds to the minus 1 just to emphasize how my units actually do cancel. So seconds cancels with 1 over seconds. And that will give me just joules for my final answer. And those I can just type right in. Then typing that in, we get 4.66 times 10 to the minus 19 joules there. Okay, so to answer this, we can look at whether these photons have enough energy. So we know from the previous one that the threshold wavelength is 427 nanometers. That sets the amount of energy that the threshold or binding energy was. The question is, what does this photon have, right? If the energy of a photon is greater than the binding energy, then electrons are going to be ejected. So that's the question. Does this photon have more energy than the energy of a photon with 427 nanometers? And the answer is yes, because, again, energy of photon is equal to hc over lambda. And so this is a shorter wavelength photon, so it has more energy than a photon with 427 nanometer wavelength because of that inverse relationship. So yes, we should see an electron ejected. And what is the kinetic energy? Well, that we can go back to our key equation. E photon is equal to W plus the kinetic energy of the electron. And so energy of the photon I don't know, but I can always go back and forth. I know the wavelength. I'll be able to turn that into the energy. So I'll know the energy of the photon. I already know the binding energy from the previous part. And the kinetic energy is what I'm solving for. So solve for kinetic energy. We do that by subtracting W from both sides to get kinetic energy by itself. So our answer here is going to be E photon minus W is equal to the kinetic energy. Remember that kinetic energy is going to have to be positive. So if this answer here is correct, we should see kinetic energy of the electron positive when we go and do this. Okay, then let's try it. First, let's get the energy of our photon. So the energy of the photon is equal to 6.63 times 10 to the negative 34 joule seconds times 3 times 10 to the 8 meter per second. Just getting that in on the edge of the screen here. Our wavelength, 401 nanometers, which we have to convert to meters, so 401 times 10 to the minus 9 meters. Okay, I'm not going to show the calculator on this one, but I did it. E photon is 4.96 times 10 to the minus 19 joules. W is 4.66 times 10 to the minus 19 joules. So yes, we will see a photon ejected because this is bigger than the binding energy. 4.96 versus 4.66. Then just plug in and we'll get our final answer. 4.96 times 10 to the minus 19 minus 4.66 times 10 to the minus 19. Kinetic energy is an energy, so it is going to be in joules. That's correct. And our final answer is 3.0 times 10 to the minus 20 joules is our kinetic energy. A good check here is that that is positive, so we are getting an electron ejected. Remember, kinetic energy can't be negative. Okay, for this exercise number 3, we have a transition from 5 to 3, and we want to know if the photon was absorbed or emitted. So we can think about that diagram to answer that. 1, 2, 3, 4, 5, something like this. N equals 1, 2, 3, 4, 5. In this case, we're going sort of from 5 down to 3. This is energy on the y-axis, so this is a photon emitted. The photon is losing energy, or sorry, the electron is losing energy, going from 5 down to 3, and that will cause the photon to be emitted. Now, to calculate the wavelength of the photon absorbed or emitted, the most typical equation we use in this part of the class is that Rydberg equation. 1 over lambda is equal to RH 1 over Ni squared minus Nf squared. So anytime you see the hydrogen atom, that's often the equation that you're going to need to use. Wavelength in nanometers is what we want, so that's good. That's over here. What this equation is solving for right now is 1 over lambda, so we will need to flip that over to get lambda by itself at the end of this problem. And then, yeah, we have, right, our other variables in this equation. Ni, that's the initial level. So Ni, right, I stands for initial, so that's equal to 5. And F is the final, that's equal to 3, the final state. RH is that constant, 1.097 times 10 to the 7. And the unit here is meters to the minus first. For this equation, it's often convenient to just plug in and then solve for lambda at the end. So first, we'll plug in 1.097 times 10 to the 7 meters to the minus 1. Ni is 1 over 5 squared minus Nf 1 over 3 squared. Okay, so typing all that into my calculator, here's what we get with all the parentheses and everything in there properly, negative 780088. And the unit here, always important to double check, the unit here is still meters to the minus 1. All this stuff here with the n's has no units on it. And now we're not done. We're in meters to the minus 1 right now. We need wavelength in meters, and that's because we don't have wavelength yet. We have 1 over wavelength. So one thing to think about here for solving this is that you can think about 1 over x is equal to 2. If that's your equation, it is true that x is equal to 1 over 2, 1/2. Right, that works because if I take 1 over x is equal to 1 over 2, I can basically take 1 over both sides. That will flip x back up to the top and give me x equals 1/2. You're also free to cross multiply though, right? So the other way to do this is just sort of by hand, multiply both sides by lambda and get there. So I'll show that over here. I have lambda on the bottom, so I need to multiply both sides by lambda. I'll get lambda times 1 over lambda is equal to negative 780088 meters to the minus 1. That's a good start. That gives me 1 is equal to all of this stuff times lambda. And then I just need to divide by all of that. So divide by negative 780088 on both sides. When I do that, I get lambda is equal to 1 over all this stuff, which is equal to, and I get lambda is negative 1.282 times 10 to the minus 6 meters. Now, thinking about what lambda or wavelength is a distance, right? If we think back to when we first showed it on the slides, it's that peak-to-peak distance. So it's not possible for this wavelength to be a negative number. What in this equation, the negative is just a representation of emission. So negative means emission in this equation. So we can't keep the negative in here. The actual wavelength is just 1.282 times 10 to the minus 6 meters, and the negative just means emission. Never report a negative wavelength because it doesn't make physical sense. Okay, our last step is converting back to nanometers. So we have 1.282 times 10 to the minus 6 meters. And then remember the conversion factor, which you'll get given to you on like a quiz or exam. 1 nanometer is 10 to the minus 9 meters. So I have meters. The thing that I have already needs to go on the bottom to make the units cancel. So put 10 to the minus 9 meters on the bottom and put 1 nanometer on the top. And that will have everything cancel. And when you plug that into your calculator, you should get 1282 nanometers is equal to lambda. Remember, we typically are working in the tens to hundreds or thousands of nanometers for visible and UV and near IR light, which is typically what we're using in this part of the class. If you like the other version of this conversion factor, remember that's another good way to do it. If you multiply both sides here by 10 to the 9, you get 10 to the 9 nanometers is equal to 1 meter, right? It's the same conversion factor, just keeping the negative exponents out of it. So either version of that conversion factor will work to go from nanometers back, or from meters back to nanometers.